Dear students, today's topic is electromagnetic induction part 4. Part 1, part 2, part 3 I have already discussed and uploaded on my video channel, that is on YouTube channel. You subscribe it and refer it. Now today we have to start part 4, and what you have to learn in this part 4 that you see here, I will explain mutual induction and mutual inductance, then coefficient of mutual inductance, then coefficient of mutual induction of two long solenoids. After that, recapitulation in the form of mutual multiple choice questions, that is MCQs. Now one by one I explain. The first one is mutual induction. So first you understand this phenomena of mutual induction. Mutual induction, basically it is the phenomenon of production of induced EMF in one coil due to the change of current in neighboring coil is called mutual induction. In other words, we can say that you must understand the difference between mutual inductance and mutual induction. Mutual induction is the process or the phenomena, and mutual inductance is the property of two coils by virtue of which current possesses in one coil by the induction of EMF in neighboring coil, and this whole process is known as mutual induction. So that's why we say that the phenomenon of production of induced EMF in one coil due to change of current in neighboring coil is called mutual induction. That phenomena you have to understand by this experiment. In this experiment, that we have taken one primary coil, this is secondary coil, this is battery, this is galvanometer which is very sensitive, and a tapping key. Now these two coils are placed very close to each other, means this primary coil that we place in secondary coil, so that it becomes a coaxial solenoids or coaxial coils. Now this primary coil is connected to battery, so that the current that flows through the primary coil and EMF induced in secondary coil, which opposes any change in the strength of the current in primary coil. This secondary coil that connected to the sensitive galvanometer, and then we make the connection of these primary and secondary coils with battery and sensitive galvanometer respectively, along with tapping key. So now we are performing the experiment of mutual induction by connecting the connections, and then you see what happens when we press the key and release the key. In both the cases, sensitive galvanometer will show the deflection. And you see here, when we press and release, then what happens? Galvanometer shows deflection. So by pressing and releasing the key, the galvanometer shows a deflection. You can see here. So it means the current is flowing through the primary coil, and due to the change in the current in the primary coil, change in magnetic flux linked with the primary coil, since secondary coil is very near to the primary coil, so due to induction, magnetic flux, change in magnetic flux linked with the secondary coil, and hence an EMF is induced. So in secondary coil, when the EMF induced, then hence current is also induced. So you can see here also in the diagram, current is flowing through the primary coil. So increase in magnetic flux linked with the primary coil. Since secondary coil is near to the primary coil, so magnetic flux linked with the secondary coil also increases and an EMF is induced, hence a current is also induced, whose direction is given by arrow 1. When we release the key, then what happens? Magnetic flux linked with the primary coil decreases and hence with secondary coil also decreases, and direction induced is represented by arrow 2. So that's why we say that mutual induction is the production of induced EMF in the secondary coil during the time of make or break of current in the primary coil, and that phenomena is known as mutual induction. So by this experiment you can understand the phenomena of mutual induction. Now we have to understand mathematically the things which we have explained in the experiment. I already explained you the mutual inductance. It is the property of two coils by virtue of which each opposes any change in the strength of current flowing in the others is called mutual inductance between the two coils. Now we have to find out the coefficient of mutual inductance. Similarly, as you have done in case of the self-inductance, only the difference is that here there are two coils and in self-inductance only the one coil. So we say that let I is the current flowing through the one coil at an instant and phi be the magnetic flux linked with nearby coil at that instant. It means more and more current flowing through one coil, then more and more magnetic flux linked with the nearby coil. So we can say that phi directly proportional to I, or for omitting this proportionality sign, we require a constant, and that constant is M. And this M is called constant of proportionality and is known as mutual inductance or the coefficient of mutual inductance of two coils. If we say that I equal to 1, then M equal to phi by using this equation, and we can define it like that. Coefficient of mutual inductance of two coils is numerically equal to magnetic flux linked with one coil when unit current passes through nearby coil. We also know that induced EMF E equal to minus N d phi b upon dt, but phi b equal to Mi. So you substitute the value here, and when you substitute the value here, then you will get minus M di upon dt for the number of turns 1. So here this N equal to 1, where N is the number of turns of the coils. So in that condition, E equal to minus M di upon dt. So if we say that di upon dt equal to 1, then M equal to induced EMF. So again we have to define in the similar way. Thus the coefficient of mutual inductance of two coils is numerically equal to EMF induced in one coil when rate of change of current is unity in nearby coil. And the units of mutual inductance, SI unit of mutual inductance on the honor of name of scientist Henry, and by using this equation, M equal to phi upon I, and phi is measured in Weber, I is measured in ampere, so that's why it becomes Weber per ampere. Another unit we can find out from here, E equal to minus M di upon dt, then M equal to E upon di upon dt. So from here we can say that volt second per ampere. So these are the units of mutual inductance. Now, coefficient of mutual inductance of two long solenoids. So for that purpose, we consider two long solenoids S1 and S2 having the radius R1 and R2 respectively and the number of turns N1 and N2 respectively, and they are of equal length represented by small l. Now we say that I2 current is passing through the solenoid S2, then the magnetic flux linked with S1, and that magnetic flux is N1 phi 1 equal to M12 I2, where M12 is the mutual inductance of solenoid S1 with respect to S2. It also referred as the coefficient of mutual induction, right? So mark this equation 1. Now when current I2 is passes through the solenoid S2, then a magnetic field is developed, and that magnetic field B2 equal to mu naught N2 I2, already you have studied, where N2 is the number of turns per unit length of solenoid S2. Then the resulting magnetic flux linked with the solenoid S1, that becomes N1 phi 1 equal to N1 B2 A1. N1 B2 A1. N1 is the number of turns of the solenoid S1. A1 is the area of cross section of solenoid S1. B2 is the magnetic field produced by solenoid S2, and S1 is in the magnetic field of solenoid S2. So that's why magnetic flux linked with solenoid S1 is N1 B2 A1. Now substitute the values. What you will get? N1 phi 1 equal to, in place of capital N1, N1 L, that is total number of turns in solenoid S1, area of cross section pi R1 square, and magnetic field B2 mu naught N2 I2. Then we solve it. Then we get mu naught N1 N2 pi R1 square L I2. Mark this equation number 2, where N1L is the total number of turns in solenoid S1. Now from equation 1 and 2, their left hand sides are equal, so we can substitute the value of right hand side this. M1 2 I2, that is equal to mu naught N1 N2 pi R1 square L I2. Now from here you see that this I2 and I2 get cancelled. You will get M12 equal to mu naught N1 N2 pi R1 square L. That mark equation number 1. Similarly, when a current I1 passed through the solenoid S1, then the flux linked with the solenoid S2, that becomes N2 phi 2 equal to M21 I1, where M21 is called the mutual inductance of solenoid S2 with respect to solenoid S1. Then, because the current is passes through the solenoid S1, that is I1, therefore the magnetic field due to the current I1 in the solenoid S1, that can be written as B1 equal to mu naught N1 I1. Right? Now, the important thing is over here. The flux due to current I1 in S1 can be assumed to be confined solely inside S1, because S1 is kept inside the solenoid S2. Since the solenoids are very long, thus the flux linked with the solenoid S2 can be written as magnetic flux linked with solenoid S2 equal to N2 phi 2 equal to N2 B1 A2, right? But what condition we are taking here? The flux due to current I1 in S1 can be assumed to be confined solely inside S1. So that's why we have to write in place of this A2, that is pi R1 square, because the area of the solenoid S2 is equal to the area of cross section of solenoid S1, because the magnetic flux due to the current I1 in S1 is only confined in the solenoid S1. So that's why N2 phi 2 equal to, in place of N2 is N2L, and in place of A2 we have to write pi R1 square. In place of B1 we write mu naught N1 I1. Mark this equation number 5, where N2L is the total number of turns of S2. Then from equation 4 and 5, this is equation 4 and this is equation 5. Then from here what you will get? You will get M21 equal to mu naught N1 N2 pi R1 square L. Mark this equation number 6. Now you see that the equation 3 and 6 both are the same. So that's why using the equation 3 and 6 we get M12 equal to M21 equal to M. Right? Now if medium of relative permeability mu R had been present, means inside the solenoids there is a medium of relative permeability mu R, then in that condition mutual inductance would be M equal to mu R mu naught N1 N2 pi R1 square L. So this is coefficient of mutual inductance of two long solenoids or the two coaxial solenoids. The important point is here that the flux due to current I1 in the solenoid S1 can be assumed to be confined solely inside S1. So that point you have to keep in your mind. Now, there's some recapitulations in the form of the multiple choice questions. The first one is the mutual inductance between two coils depends on the first option, that is A, medium between the coils, separation between the two coils, orientation of the two coils, all of the above. So you apply your concept what you have learned it, and then find the answer. Answer is here, that is answer D. Mutual inductance between two coils depends on all the three factors given here. Now the second multiple choice question, mutual induction is the production of induced EMF in a coil due to change of current in the, options are here, same coil, neighboring coil, both A and B, and D option, neither A nor B. So from the definition, if any change in the strength of the current in the neighboring coil, then an EMF is induced in another coil. So that's why answer should be B, that is neighboring coil. Now the third question, as shown in the figure, P and Q are the two coaxial conducting loops separated by some distance. As you can see, when the switch S is closed, then clockwise current IP flows through P coil. as seen by E, and an induced current IQ1 flows in Q. The switch remains closed for long time. When S is opened, means switch is opened, a current IQ2 flows through Q coil. Then the direction of IQ1 and IQ2 as seen by E, means this is the observer who is observing R. First option is respectively clockwise and anti-clockwise. Option B, both clockwise. Option C, both anti-clockwise. Option D, respectively anti-clockwise and clockwise. Apply the concept, whatever you have learned, and then you check your answer, and the answer should be D, respectively anti-clockwise and clockwise. Now the fourth question, mutual inductance of a pair of coils, each of n turns in, is M Henry if a current of I ampere in one of the coils is brought to 0 in t second. Then EMF induced per turn in the other coil in volt will be. So you have to calculate it by using the formula E equal to minus M di upon dt. Apply the concepts, solve it, then you will get answer A. So answer A is correct. Similarly, fifth question, the mutual inductance of a pair of coil is 0.75 Henry. If current in the primary coil changes from 0.5 Henry to 0 in 0.01 second, find the average induced EMF in secondary coil. So apply the concept. Formula is simple. E equal to M di upon dt. Each and everything is given here. Substitute it and find out the answer. Your answer should be D. Now, sixth question. The mutual inductance M12 of coil 1 with respect to the coil 2. Your options are here. Increases when they are brought nearer. Option B, depends on the current passing through the coils. Option C, increases when one of them is rotated about an axis. Option D is the same as M21 of coil 2 with respect to the coil 1. So whatever you learn, you apply your concept, find your answer. Your answer should be A and D. If you like my video, then like it, subscribe it, press the bell icon. Thank you and have a nice day.